Welcome to CS 1401 Video 14.2. In this video, I'll take the algorithms from Video 14.1 and implement them in Java. Remember that a recursive algorithm is an algorithm that calls itself to solve successively simpler problems until it reaches a problem that it can solve immediately. The call to the algorithm itself to solve the simpler problem is the recursive case, and solving the problem immediately is the base case. For each of the algorithms, I'll have recursive cases and base cases. Let's start with the algorithm for the function to calculate factorial of n. Here's my pseudocode algorithm. If n is less than 2, return 1. That's the base case. Else, the recursive case is return n times fact of n minus 1. To implement this in Java, I'll translate the pseudocode algorithm into a Java method called fact, which will take an integer argument for n and return an integer value for the result of fact of n. With the recursive implementation of fact, I can pretty much just copy the pseudocode as the algorithm. If n is less than 2, return 1, which is the base case, or else return n times fact of n minus 1, which is the recursive case. I'll also write a little driver as main so that I can test my code for fact. The driver reads an integer argument from the command line. That's going to be the factorial method's argument n. Checks to make sure that the value of n is a valid value for the factorial function. And if the value is okay because it's non-negative, prints out the result of calling the fact method with argument n. The code in the driver consists of things we've seen many times before. This is just a way to call fact. The interesting part of this program is the method fact, which is recursive. Note that the recursive call to fact looks just like the call to fact in main. There's nothing special about a recursive call. It's just another call to the method. Another interesting thing about the method fact is how simple it is. A direct expression of the definition of factorial. We can see right away that the method will be correct. One interesting thing to note about this code, like all the code I'll present in this video, is that it doesn't have any assignment statements at all. This means that for any activation record of this function, a variable can get instantiated with a value, but once instantiated, the value of a variable never changes. Things happen in the program because successive recursive calls to the method return different values. Next, I'll compile and test fact. First, I'll compile factorial. And now I'll run it with a succession of values. So let's start with one which we know isn't going to work. And I'm happy to say that my program caught it. Let's now try looking at the start of the factorial definition. And factorial of 0 is in fact 1. Factorial of 1 is also 1. Factorial of 2 is correctly 2. And now let's try factorial of 3, and we got 6. Well, factorial actually goes up pretty fast. Let's try factorial of 10. And that's a pretty big number. The next arithmetic algorithm I wrote was for mod, which calculates the remainder in integer division. Here's the pseudocode from Video 14.1. Mod takes two arguments, n and m. If n is less than m, then I return n. That's the base case. Else, I return mod of n minus m and m, which is the recursive case. Again, this is basically just the definition of the modulus function. Here's my implementation of mod in Java, and just like my implementation of factorial, the Java code is pretty much just copied from the pseudocode. I've also written main as a driver for mod. Main reads two arguments, n and m, and prints out the result of calling mod of n and m. Let's compile and test mod. I'll compile my program. And then I'll run it with some examples whose values we know as a result. So, for instance, 13 and 10 correctly returns 3. 7 and 2 correctly returns 1. And let's also check it for 29 and 5, which correctly returns 4 because 29 minus 25 is 4. In video 14.1, I also wrote a recursive algorithm for calculating the nth Fibonacci number. The Fibonacci sequence is 0, 1, 1, 2, 3, 5, 8. So starting with n equals 0, fib of 0 equals 0, fib of 1 equals 1, fib of 2 equals 1, and so on. Here's my pseudocode algorithm, which basically directly expresses the definition of the Fibonacci sequence. Fib takes an argument n. If n is less than 2, I return n. Else, the recursive case, I return fib of n minus 1 plus fib of n minus 2. The base case works because fib of 0 is 0 and fib of 1 is 1. And after that, fib of n equals fib of n minus 1 plus fib of n minus 2. Here's my Java implementation of fib. Again, the Java code is pretty much exactly the same as the pseudocode. The method takes an integer argument n. Just as in the pseudocode, if n is less than 2, then the method returns n. Otherwise, it returns the sum of fib of n minus 1 and fib of n minus 2. I also wrote main as a very simple driver for fib that prints out the result of calling fib with the value of the argument that the user enters on the command line. Next, I'll compile and test fib. I'll compile Fibonacci, and I'll run it with some values that we know. So let's start with the base cases. That one's right. Fib of 1 correctly turns 1. Fib of 2 is also 1. That's right, because it starts out 0, 1, 1. Fib of 3 is 2. And fib of 4 is 3. Let's try fib of 10. And sure enough, it's correctly 55. So far in this video, I've been implementing algorithms for arithmetic functions. That is, these algorithms return a value. Now I'll turn to the implementation of algorithms for procedures, algorithms that have side effects like printing out something but that don't return a value. The first algorithm I'll implement will be countdown, which prints on a single line the integers from n to 1. Here's my pseudocode algorithm from video 14.1. The algorithm countdown takes an integer argument, the number. If the number is greater than 0, then I print the number and then call countdown of the number minus 1 to print the numbers from the number minus 1 down. That's the recursive case. Or if the number is not greater than 0, I've reached the last number and I print a new line. That's the base case. So basically the idea is to print the number, then print the numbers below that. When the algorithm reaches 0, it prints a new line, which is the base case. The Java implementation is basically just a straightforward copy from my pseudocode algorithm. The method has a return type of void because it doesn't return a value at all. The body of the method checks to see if n is greater than 0, which is the recursive case, in which case it prints n and then calls countdown of n minus 1. If n is not greater than 0, we've reached 0, which is the base case, and the method prints a new line. I also wrote main as a very simple driver that calls countdown with the value of the argument that the user enters on the command line. Let's compile and test countdown. I'll compile my program, which I called countdown R for recursive. And now let's try calling it with a series of test values, starting with 0. And it doesn't print anything, which is exactly what we expected, just the new line. Let's try it with 1 to see if that base case works. Yes, it does. And then let's try it with 2. So far so good. Let's be brave. We'll try with 8. And it prints out exactly as expected. Finally, here's my Java implementation of COUNTUP. You recall from video 14.1 that COUNTUP is simply count down with the order reversed between printing the values and the recursive calls to print the remaining values. Here's my pseudocode for COUNTUP. Note that in this algorithm, the recursive call comes first, thus printing the numbers smaller than n, and then prints n. When n reaches 0, that's the base case, and the algorithm stops recursing. You may have noticed something odd about this algorithm. It prints the numbers going up from 1 to n, while successively recursing with the numbers going down from n to 0. We get this result precisely because the recursive call comes before the print statement. You can think of the printing occurring as each activation returns control to the activation that called it. So here's the Java implementation of COUNTUP, which looks just like the Java code for COUNTDOWN, with the statements for recursive call and print in reverse order. As in the pseudocode, I've made the base case implicit. If n equals 0, then do nothing, just return. I have the driver in main print out a new line so that the output looks nice. Let's compile and test COUNTUP. I'll compile COUNTUP in its recursive version. Let's try COUNTUP of 5. And it produces exactly the output we were expecting. So that's a look at implementing recursive algorithms for arithmetic functions and print procedures as methods in Java. In the videos for the next class, we'll gain additional experience with recursive algorithms. See you then.